Today I'd like to talk about shale gas. I'd like to tell you a bit about what it is, what hydraulic fracturing is, and horizontal drilling. I'm going to tell you a little bit of a story about our research. Last year we published the first paper examining interactions of water quality with how near people are to natural gas wells. My life has never been the same since then. And I want to talk about the process of science too. My clock's still not running. The process of science, and ultimately I want science to be useful. So I'll tell you and give you some examples today about how to make our science as useful as possible. That's the goal. Still off, but someone just signaled me. All right, fracking and the future of gas. When I talk about gas today, I'm talking about natural gas, not gasoline. So if we discuss gasoline, I'll call it by name. All right, here's a Time magazine article from last year. This rock could power the world. What is it that's so amazing about unconventional energy resources? Well, 5 years ago in this country, we were talking about building import terminals to bring natural gas from overseas to the United States because our production of oil and gas has been declining for many, many years in this country. Today, we're talking about building export terminals to take gas from the United States to other parts of the world, an absolutely transformational event. And this is primarily due to newly identified resources of unconventional energy, particularly oil and natural gas. These sources of energy are made available by two processes that I'll talk about briefly: horizontal drilling and hydraulic fracturing. All right, what is hydraulic fracturing and horizontal drilling? Well, first of all, unconventional sources of oil and gas are different. In the old days, you drilled a hole in the ground and the oil and the gas came bubbling up. So that's a conventional source. It might have been gas or oil that was built up in an anticline, in a dome, if you will. So you punch down a hole into that dome and the things flow to the surface. In unconventional oil and gas, either in sand or shale, the oil or gas stays in there. It's caught tightly in rocks. So it's there, but you can't make it flow to the surface. So in the last decade in particular, new technologies, really amazing technologies, have made that energy available to us. Two processes do that: horizontal drilling. Horizontal drilling, as you can imagine, going down a mile or more for your drill, but then going sideways. So you can think of shale gas, for example, as a cake. So I love cake. I love icing. So I've already scrubbed all the icing off the top of the cake, and all that's left is that little thin layer down there in the middle. And if I drill a hole down into that cake, I only intersect a tiny little bit of that icing. But if I have the capability to drill down into the center of that cake and then go sideways through that layer, now I'm in business. And that's the business that the oil and gas companies are in today. Through amazing technologies, three-dimensional technologies, they can find a shale layer that might be only 100 feet deep, a mile or more underground, and track that layer three-dimensionally for a couple miles sideways. That's the horizontal drill part that really makes this possible. But there's something else that you have to do to get this oil and gas out of the ground, and that's the step of hydraulic fracturing. So even if you can drill through that little layer of icing or shale, you can't get the gas to flow back to the surface without cracking open that rock. And that's hydraulic fracturing. So for each shale gas well, for instance, companies inject 2, 3, 4, 5 million gallons of water per well, load it up with sand and other chemicals, and pump that underground under pressures that are similar to or even greater than what you find in the deepest part of the earth or the oceans, the Marianas Trench, for instance. So 7,500 pounds per square inch, for example. So very high pressures to crack open these rocks that allow that gas and oil to flow into the wellbore along and up to the surface. So that's what makes shale gas, tight sands, and other things possible, is the combination of these two events. Both steps have been around a long time. Hydraulic fracturing goes back to the 1940s, horizontal drilling to the 1980s at least. But the combination of a horizontal drill miles long and very high pressures of hydraulic fracturing are new. Another thing that's so amazing about this transformation is that there are shale plays and oil plays and sand plays and gas plays all over the country. This revolution began in Texas in the Barnett Shale, quickly spread to other areas of Louisiana, Texas, Oklahoma, Arkansas. And the biggest play in the country is where we've been working for the last few years. That's the Marcellus Shale in Pennsylvania, Ohio, West Virginia, and New York. Now, with all that optimism, then I get out of my car to sample someone's house in Pennsylvania, and you see signs like this. So what is it that causes the opposition to this process? And why does that opposition occur? This process of shale gas extraction and all the economic benefits that it brings also divides communities. So I've sampled homes where fathers and sons no longer speak to each other because of the way they disagree over drilling and the process. So it really does divide communities. Our goal for this work from the beginning was to look at potential environmental problems, to ask where they occur, if they occur, what can we do about them and how to solve them. So we don't lobby against shale gas, we don't call for bans on these processes. We're interested in problem solving. This is a map of the state of Pennsylvania. So the first commercial oil well in the world was drilled 150 years ago in Titusville, Pennsylvania. Since that time, 400,000 or so wells have been punched into the ground in Pennsylvania, most of them in the western part of the state. But the shale gas revolution, and where we've been working, has especially been rapid in the northeastern part of the state, where there hasn't been as much oil and gas extraction in the past. These are relatively rural areas. These are quite poor areas. So the economic benefits of this extraction for people have been great. All right, so what did we do? Well, starting a couple years ago, myself, my colleague Avner Vengosh, and other folks at Duke, we started sampling people's water. We sampled people on private water wells, because if you're on a private water well, you don't have testing of your water. EPA doesn't regulate your water. No one checks the quality or the safety of your water. That's the kind of well that I have in my house here in rural North Carolina. So we targeted people on water wells. We've now sampled over 200 homes in that area. We contact them, we walk up their driveway, we grab a sample of water. This is a picture of Nat Warner, a graduate student from Duke University. We bring those samples back to the laboratory at Duke and analyze them for a whole series of constituents. Now in this project, we've asked one simple question. That question is, if you're living near a natural gas well, is your water any different? Some of the measurements that we take, this is a mass spectrometer that's at Duke. We analyze the isotopic, or sort of the chemical signatures of compounds. Carbon, hydrogen, oxygen all have different forms, if you will, in the environment. There's low levels of radioactivity found deep underground in the Marcellus region. So we have the ability to look for that, if there's any evidence of that escaping into surface waters. There are brines and salts. Water that's found deep under the earth is really pretty nasty in most cases. It's full of salts and many other things that can be harmful. So you want to separate that. You want to keep that from getting into the water that's up near the surface. So we analyze all these things and many more at the laboratory at Duke with other colleagues, and also in other locations too. All right, what did we find? Well, a year ago, as I mentioned, we published the first paper looking at the relationship of water quality and distance to gas wells. There are a lot of things, first of all, that we didn't find. We have not to date found any evidence at all for the things that people are concerned about most, and that's the chemicals in fracturing fluids. Those chemicals include benzene, they can include diesel, many organics that are toxic to people. They can include acids like hydrochloric acid. These are things that are put into the fluids to help change the viscosity, increase the flow, as biocides to reduce microbial activity, acids to dissolve carbonates and things to make the pore space greater so that gas and oil can flow up to the surface. But we didn't find any of that. We didn't find radioactivity. We haven't found any evidence for the brines from deep underground that using the isotopic signatures. But we did find one thing. And that one thing was much higher dissolved gas concentrations if you were living near a natural gas well. So methane is natural gas. It's the dominant constituent in gas. So we found a lot more methane and more ethane and propane if people were living within a kilometer. So on the x-axis of this figure is in thousands of kilometers. The y-axis is the concentration of methane, and the gray band is the level of concern, if you will. So any values within that band are recommended to consider taking action, and anything above that band, that threshold of 28 milligrams per liter, we're recommended taking immediate action. So the only values you see above that threshold are people within a kilometer. Those are dangerous values in some cases, if that air builds up in a confined space, such as a basement or a shed. So clearly there's something going on here with distance to gas wells. This is a glass half empty, glass half full kind of story. Most of the things that people really care about we didn't find. But we did find a strong interaction with gas concentrations. Why? We also used isotopic approaches, fingerprinting approaches, if you will, to ask, all right, if there's more gas there, where did it come from? Was it generated by microbes in shallow layers? Was it generated far underground millions of years ago under high heat and pressure? And science, chemical isotopic signatures, give us the tools to be able to distinguish those things. And where we had high methane concentrations, we also had isotopic signatures that look more like gas that's found deep underground, not generated by microbes. Microbes also don't generate ethane and propane. Yet we had more ethane and propane in the water too. So not a problem everywhere, and in no sense, just because a person's living within a kilometer, does that mean they're going to have a problem. But where problems occurred is where people were close to gas wells, and we want to do something about it. Now, I've argued from the beginning that this shouldn't have been a surprise. This is a map of Pennsylvania. Everywhere you see a push pin on this map, that's a case of documented stray gas contamination over the last decade or so. There are dozens and dozens of these things, and they predate the use of horizontal drilling and shale and hydraulic fracturing. All right, so if you look at industry data, the mining service in the U.S., Schlumberger, 10 to 20% of the wells can have problems with casing, with the cementing around them. As the wells age, that value can jump to 20, 30, even 40%. So this is a problem we actually know about. And that really is important. So what's the mechanism of what's going on? Because by understanding the mechanism, we can fix the problem, I believe. So the thing that people worry about most is that step of hydraulic fracturing. Is it possible that a mile underground, that the pressures that are generated that open up cracks in the ground actually make those cracks go all the way up to the surface through the rock? Now that's the worst case scenario, because then you have a direct connection between the toxins and the chemicals in those fluids and people's drinking water. Now we don't know the mechanism, to be perfectly honest, we don't know. But I don't think that's likely at all. It's not likely for many reasons. It's possible that natural fissures and cracks in this area could be connected to those, and you could have some hydraulic conductivity. But that's not where I would start. From the beginning, we've suggested that starting with the simplest thing, which I think is also true in science. That's with the casing and the cementing. So when our paper came out, we made some recommendations. There's a presumptive liability rule in the state that says if you're living within 1,000 feet of a natural gas well and you have a problem within 6 months, the company is presumed guilty unless they can show that they didn't cause the problem. That's a great rule because it means companies pay for water testing, protects the people. If their water turns bad, protects the company from paying for low quality water that they didn't cause. So we recommended, for instance, that distance be expanded to 3,000 feet. Pennsylvania in February just passed a law expanding that to 2,500 feet. So a number of examples like that. We want to take our science as best as we can understand it and make it useful to make these processes safer. All right, there's a case going on right now that's perhaps even more controversial than ours has been. That's the case of Pavillion, Wyoming. Some of you have heard about this. Now in Pavillion, the EPA has suggested that they believe they found evidence for the chemicals, the organics, things like benzene, in the drinking water, in these shallower layers. So there's a lot of testing going on, checking of this. This case is a little bit different. Now here's a case where the hydraulic fracturing was only 1,500 feet from the surface, and the drinking water well is as deep as 750 feet or more. Now that's probably not what we want to do. It's too close, sometimes in the same formations. All right, so there's a lot of work being done in this area. Not sure about this case yet, but I think ultimately it will stand up. Okay, a few other concerns. People are worried about the water. So every well, as I mentioned, takes 2, 3, 4, 5 million gallons. Where will that water come from? How do we keep track of that water? The wastewater, I believe, the water that comes back out of the well after the extraction starts, is one of the biggest concerns. So you pump in 3, 4, 5 million gallons with chemicals, you get this surge of water back up that's a mixture of what you put down in the ground and this naturally pretty nasty water. You've got to do something with that water. You can't release it into the surface streams. You don't want to go into a municipal water treatment plant because they're not set up to take the volumes or the chemicals that these plants hold, these waters hold. So you can either send them to a private treatment facility, which has sprung up in Pennsylvania, or you can deep inject them, pump them back deep underground where the water's already pretty nasty. So that's what's happened. Both those things are used now. You probably have heard recently in the news that there have been links between tremors and small earthquakes between that deep injection step. That's because you're pumping high volumes of water underground at very high pressures and causing the rocks to slip against each other. But those two things are better. Private water treatment, deep underground injection, and kudos to industry for a new step, and that is to try and reuse or recycle that water. So if you can take wastewater from one well and use it to hydraulically fracture the next well, you reduce the amount of water required, you reduce the amount of waste that's generated. So I think this is where we want to go. Another thing that we've been working on, as my last example, is air quality. So it's not just about the water, it's about the chemicals that are volatilized and that flow into the air from the wastewater ponds, from the extraction process during the well completion and during the transmission of natural gas. There's a controversy going on right now about how much better natural gas is than coal in terms of its greenhouse gas emissions. Now, natural gas is better than coal. There's no mercury. All right, for things like sulfur dioxide, for particulates, there's no doubt the natural gas is better than coal. But we don't have a good sense for how much methane leaks out while we're mining the natural gas and while we're moving it along pipelines. So here's the last research example I'll give you. We have a Google Street View project, if you will, brand new technology, first of its kind, mapping every street in the city of Boston for their natural gas leaks. So imagine a high-resolution instrument in a car to measure methane in real time, high-resolution GPS unit. You drive every street, every block in the city, 10, 15 miles an hour. When you get a plume of methane, we jump out of the car, grab a sample, put it in a bag, take it back to my laboratory here at Duke, and analyze it for its isotopic composition. This is work with colleagues, friends at Boston University, Nathan Phillips, and also at Harvard. This gives us a real-time map of leaks and whether that gas is coming from a landfill, a sewer, or natural gas, again, because of its chemistry, its isotopic composition. This is the kind of picture that you see. You have some blocks where there are no leaks at all, and other blocks where there are methane concentrations, in this case, 10-fold higher than background. And if you look at the city as a whole, we've mapped about 2,000 or 3,000 leaks across the city. Now, the point of this isn't to say we shouldn't be using natural gas. The point of this, again, is to use the science to help solve the problems. So if we can draw attention to where these leaks are, more of those leaks are going to get fixed. So we'll reduce the greenhouse gas emissions, we'll reduce potentially some fires, and even save some human lives. That's probably the first research project I've ever done where I've been able to say that. So again, making our science useful. Well, finally, I'd like to finish with just thinking about where our energy comes from, because sometimes in the environmental sciences, we get focused on the warts of different things. Every form of energy that we use has some problems. So I said in the beginning, we've never called for a ban on hydraulic fracturing, because no one's told me where else the energy will come from. When I get on a plane and fly from Raleigh-Durham to Pennsylvania to do our sampling, I look out my window, this is what I see. I see mountaintop mining all across states like Kentucky, Virginia, West Virginia. That is a nasty way to get your energy, with enormous consequences for air, for water quality, for waste. That's not what we want. With coal use, we get things like sludge spills. This is the Kingston, Tennessee spill. 2 trillion pounds, 1 billion tons of waste broke from a containment and flooded a city of 15 homes. All right, so that's an alternative to shale gas. So I think shale gas is better than that. It's amazing things going on with nuclear. Nuclear's shutting down before our eyes. Japan used to have 54 operating reactors, now it only has 2. Germany, Switzerland, Belgium are shutting their nuclear plants. 3 years ago in the US, we had over 20 plants proposed. Now we're down to at most 4 in the next decade. Now you may think that's a good thing, but if you're interested in tackling the climate change problem, that makes our job harder. And finally, there are renewables, of course. The scale of renewables is getting better. Solar voltaics, concentrated solar out in the deserts, and wind too, one of my personal favorites. Denmark now generates 30% of its electricity with wind. Why can't we do that? There is progress being made in this country. There are 10% of the states, there are 5 states in the US that now generate at least 10% of their electricity from wind. We can do this. So in summary, from an economic standpoint, shale gas is absolutely transformational. It's abundant, it's domestic, and it's cheap. It's creating jobs. It's jump-starting chemical manufacturing in this country. And if we use it to shut down coal plants, especially some of the older coal-fired plants, that's good for the environment too. But shale gas is still a fossil fuel. All right, its pollution still heats the earth and acidifies the oceans. So the point of a TED conference like this, we're instructed to dream. And I believe that for you high school students here in the audience, that you'll live to see a time where the earth is powered by renewable sources of energy, where climate change is defeated, and where air pollutants no longer kill hundreds of thousands of people every year. That's the vision. That's the dream. It may take 25 years, it may take 50 years, but I think we'll do it. You'll see it. Our health, maybe even our survival, depends on it. Thank you.